Welcome back to the course Advanced Characterization Techniques for Nanomaterials. This is Dr. Thirumalrao Gurugubelli, Associate Professor and Head, Department of Basic Sciences, SR University, Warangal, India. In this session, we will discuss one of the most advanced and powerful analysis method using X-ray diffraction. It is known as Ritweil refinement. Unlike conventional peak-by-peak analysis, Ritweil refinement uses the entire diffraction pattern from structural fitting and quantitative analysis. This technique was developed to obtain highly accurate crystallographic information from powdered materials. Let us first understand the basic concept. In normal XRD analysis, researchers often identify phases by comparing peaks, position, and intensities. However, when material contain multiple phases, overlapping peaks, lattice distortions, preferred orientation, or structural defects, or simple peak analysis become insufficient. This is where Ritweil refinement become extremely important. The method works by generating a calculated diffraction pattern based on the assumed crystal structure model. This calculated pattern is then continuously refined until it closely matches the experimentally observed data with the calculated data. The difference between the experimental and calculated pattern is minimized mathematically using least square fitting algorithms. Now, observe the diffraction profile shown in the center of the slide. You can see here the black points represents the experimental data of diffraction pattern. Red line corresponding to the calculated profile obtained from the refinement model, and the blue line is the difference profile between the calculated and experimental values, which indicates that deviation between the experimental data and calculated data is very minimum. A good refinement procedure that produces a very small difference profile at low reliability factor. The reliability factor indicates the quality of refinement. Now let us discuss the refined patterns listed on the left side. So if you see here, using the Ritweil refinement, researchers can determine the crystal structure, the lattice parameters, atomic positions, phase transaction, phase fractions, microstrain, lattice crystallite size, preferred orientation, and background contributions. These all we can calculate using this Ritweil refinement method. There are several refinement methods. So one can use any method, but the refinement process is almost same. This makes the method extremely powerful for structural characterization. One of the major application of Ritweil refinement is phase quantification. The phase quantification is very important to understand the complete structural profile of the material. For example, In multi-phase materials such as composites, the catalysts or ceramic materials, several crystalline phases may coexist simultaneously because the people are doing binary and ternary nanocomposites, where two or three or more phases will be involved in the crystal structure. The phase quantification equation source here allows us to estimate the weight percent of each phase using the scale factor obtained during the refinement. The phase quantification equation, that is W is equal to SI ZI MI by rho I VI. That is the individual scale factor of the phase 1. Z is the number of formulas units. M is the molecular weight, rho is the density, and V is the unit cell volume. So using this equation, we can find the weight percent of the each phase. This is especially useful in photocatalysis, perovskites, energy materials, and nanocomposites where phase composition strongly affects the performance. Now, look at the refinement workflow source here. The refinement workflow, first we have to import the data, then background subtraction need to be done, then we need to fix the peak fitting, then select one crystal structure file, then refining lattice parameters, then adjusting the atomic positions and minimizing the residual error. That is very important. After that, the refinement quality is evaluated using goodness of fit indicators such as RWP, that we called weighted profile R factor. Then the chi-square value. Chi-square value is that as much as less the chi-square value, the profile refinement is that much quality. So lower the chi-square, higher the quality of refinement. So the lower values indicates better agreement with the experimental and calculated patterns. Another important advantage of refinement is it can detect very small structural changes within the material, which may not be visible through a simple XRD analysis. For example, lattice distortion or cation substitution or oxygen vacancies, structural disorders or microstrain induced in the sample can all influence the refinement results. This technique is therefore widely used in advanced nanomaterials research, solid state chemistry, semiconductor research, energy storage systems, and photocatalysis. In modern material science, ritual refinement is considered as essential tool for extracting accurate structural information from the diffraction data. The key takeaway from this slide is the ritual refinement transforms the diffraction pattern into precise structural information with high confidence and quality accuracy. One more important thing here is the crystallinity, defects, and peak fitting shifting in the XRD patterns. So when we introduce the dopant, or when we make a composite, generally the peak shifting will be takes place either towards the higher angles or lower angles. That indicates the key change in the property. So the crystallinity defects and peak shifting will able to understand how XRD can be used to analyze, and even very small changes in the diffraction peaks can provide extremely valuable information about the internal structural formation and the crystalline structure of the material. Let us first discuss about the crystallinity estimation. As the crystallinity represents the degree of structural order present in the material. Highly crystalline materials produce a sharp and intense diffraction peaks because atoms are arranged periodically over the long distance. On the other hand, poorly crystalline or amorphous materials produce a broad and weak diffraction peaks due to the absence of long-range atomic order. The equation source here is commonly used for estimating the crystallinity percentage of the diffraction data. Now let us move to the peak shifting due to either doping or composition change. Particularly, the peak shifting occurs when diffraction peaks move either towards the lower angles or higher angles. This usually indicates the changes in the lattice spacing caused by either doping or induced strain or defects or vacancies created in the composite or the material. If the diffraction peak shifts towards the lower side, it generally means lattice expansion has occurred, so that the lattice parameters will be increased. This may happen when large doping ions enters into the crystal structure. Let us say the atomic radius of the doped element is higher than the host uh, crystal host atomic radius, then the diffraction peaks will move towards the lower angles. That indicates the lattice was expanded, so that the lattice parameters also increases. Similarly, the peak shifting towards higher angles indicates the lattice contraction. So which happens when the smaller ions, uh, smaller atomic radius doping elements are introduced into the host material. Also, maybe due to the comprehensive strain, that also leads to compress the lattice structure. Now, observe the oxygen vacancies, like uh, if you see the crystal diagram here, the red marks indicates the oxygen species and the blue indicates the metal ions. In between the middle, the white spots indicates the vacancies. So the oxygen vacancies are among the most important defects in oxide materials. When oxygen atoms are missing from the crystal, the local lattice distortion occurs. This distortion changes the interplanar spacing and modifies the diffraction peak position and intensities. The oxygen vacancies also influence the electrical conductivity, photocatalytic activity, optical absorption, and charge carrier transportation. So these are the influencing parameters of the material performance. Therefore, detecting these defects is extremely important in photocatalysis and semiconductor materials. Next, let us discuss about the lattice distortion and strain induced in the sample. The lattice strain caused variation in despacing throughout the crystal. This results in peak broadening and slight peak shifting, and microstrain can originate from the distortions or dislocations of the lattice atoms. The grain boundaries or dopant incorporation may be cause for the lattice distortion. So the thermal mismatch or crystal defects also one of the reason for this lattice distortion. The Williamson-Hall equation shown in the previous section we discussed that uh, helps us to separate the crystallite size and strain contributions with different peaks. Now look at the illustration showing the peak shifting due to the doping. So you can see here, the first one is there is no shift in the peak position. It is like undoped material. When it is doped with a lower atomic radius, uh, then the lattice was contracted. It is shifting towards the higher angles. In the other case, when we doped with the higher atomic radius elements, that leads to shift the peak position towards the lower side. The change in lattice parameters can be calculated by using the formula delta A is equal to the atomic lattice parameter, doped parameter minus pure parameter. And the lattice strain also can be calculated by the formula the change in lattice parameter by the lattice parameter of the pure sample into 100. That gives the percentage of strain induced in the sample when we doped the foreign elements into the host materials. This leads to a measurable peak shift in the XRD patterns. By carefully analyzing this shift, the researchers can confirm successful doping and estimate the structural modifications. So next we can discuss about the effect of defects on the diffraction peaks. How these defects influence the diffraction peaks and crystalline properties of the material. The different defects influence diffraction patterns differently. For example, the lattice dislocations increase the strain broadening. The stacking faults alter the peak symmetry. Gain boundaries contribute to peak broadening, and amorphous regions reduces the peak intensity. It means within the crystal structure, some particular region of space may be amorphous. That will minimize the peak intensity. This means the XRD is not only a phase identification tool, but also a powerful technique for defect analysis. In nanomaterials research, the combined XRD with techniques like ACM, TEM, Raman spectroscopy and XPS that provides a more complete understanding of the structural changes. That's why the structure property relationship is very important in nanomaterials research. That's why I already mentioned the no single technique is enough to understand the complete profile or properties of the materials. One of the important technique in XRD is in situ XRD. So the in situ XRD gives the real-time structural evaluation under the real-time conditions. So today we'll discuss about the fundamentals and instrumentation facility information of the in situ XRD. The in situ XRD is the most advanced characterization approach used in modern material science. The conventional XRD provides the structural information before and after the experiment. However, many materials undergoes continuous structural changes during heating, cooling, electrochemical reactions, gas exposure, or mechanical loading. In situ XRD allows us to monitor the structural changes in real time under actual operational conditions. This is extremely important because the materials often behave differently under the real working environments compared to the static laboratory conditions. Now, let us understand the experimental setup shown in the uh, in situ instrument. The X-ray beam passes through the specialized sample environment such as heating stage as a heating stage, gas chamber, electrochemical cell, or mechanical loading system. So that during the experiment, the diffraction patterns are continuously collected while the materials undergoes dynamic structural evaluations. This enables the researchers to track phase transition, lattice expansion, crystallization, chemical reactions, and strain developed in the real time. Now, look at the operant system in situ models. Particularly, the temperature dependent XRD studies structural evaluation during the heating or cooling process. And atmospheric controlled XRD investigations that gives the reactions under the different gases such as oxygen, hydrogen, or nitrogen. The electrochemical XRD is widely used for batteries and supercapacitors to monitor structural changes during charging and discharging cycles. The mechanical or stress strain XRD analysis deformation behavior of the external force that can be identified during this mechanical XRD. The liquid solution in situ XRD studies gives the information about the nucleation and crystal growth process in the real time. Now, let us observe the dynamic evolution examples shown here. If you see the bottom, the XRD patterns at different conditions was given. You can see from 0 to 1000 degrees. So the temperature was varied. It gives the in situ temperature dependent crystallite size. You can see particularly the peak between 40 to 50 degrees. The peak was simultaneously decreased with increasing the peak size, the increasing temperature. At the same time, some other peaks near 80 degrees were introduced at high temperatures. Means the crystallization, the phase transformation takes place during the heating process. By analyzing these changes, the researchers can determine reaction kinematics, thermal stability, and structural evolution of the materials. Another important aspect of this in situ is time resolution. So the modern synchrotron based XRD system can capture diffraction patterns with milliseconds, enabling ultra fast structural analysis. This makes in situ extremely useful in battery research, photocatalysis, fuel cells, shape memory, alloys, thin films, and catalytic materials. Now let us discuss about the advantages of this characterization. It provides the direct observation of structural changes during the operation. The second, it helps the correlate the structure property relationship in real time conditions. It eliminates uncertainties associated with XRD measurements. Finally, it improves our understanding of reaction mechanisms and material performance in the materials. Finally, you can say one thing that the in situ XRD enables real-time monitoring of structural evolution, allowing researchers to study materials under realistic operational conditions. Now let us discuss the important and advanced research applications of this in situ XRD facility. The in situ will give the real-time insights into the structure property relationship for smarter materials and next generation technologies. It is one of the important technique in advanced research in modern material science and nanotechnology. The in situ characterization has become extremely important because it helps researchers to observe how materials behaves dynamically under the real operational conditions. Let us begin with the battery materials. During the charge and discharging, the battery electrodes undergoes continuous structural and phase changes. In situ XRD allows the researchers to monitor phase evolution, lattice expansion, structural degradation, and reaction reversibility in the real time. This information is essential for designing high performance and long life energy storage systems. Now look at the photocatalytic part. The photocatalytic materials are exposed to light and reacts with radicals. These chemical environmental during the operations. In situ XRD helps to monitor the structural stability and phase changes during photocatalytic reactions. This enables researchers to identify active phases and understand the degradation mechanisms. Coming to the thin film or coatings, the thin film after expansion thermal stress, crystallization, oxidation, and structural rearrangement during process. In situ XRD helps to analyze the textural evolution, grain growth, and stress relaxation. This is highly important in semiconductor devices and advanced coatings. Now, coming to the perovskite materials, the perovskite materials are widely used in solar cells and optoelectronic applications. However, these materials are highly sensitive to temperature and moisture. So in situ XRD, we can find the structural stability and degradation behavior under operational conditions. This information is crucial for improving the device stability and efficiency. Then coming to the stress or strain induced in the sample, how this affects the properties of the materials. When the materials are mechanically deformed, the lattice structure changes. In situ XRD measurement provides these structural changes directly by tracking diffraction peak positions and widths. This helps the researchers to evaluate elastic deformation or plastic deformation or residual stress and fractal mechanisms. Coming to the reaction conditions, reaction mechanism, particularly in catalytic reactions, the intermediate phases may appear only temporarily during the reaction. Conventional characterization may miss these transient states because initially it will be not appears and finally it will be not appears. It will come in between and it will be disappear. But it will create a lot of disturbance to the structure. In situ, XRD captures these intermediate phases and helps researchers understand the reaction pathway and kinematics. Coming to the phase evaluation, you can see the phase evaluation diagram here. As reaction conditions change, the formation of different phases evolves with time. Tracking those diffraction phases, the transformation helps the optimization of synthesis conditions. and improve the material performance. Finally, let us discuss about the challenges and limitations of the in situ XRD. There are few challenges here. One is the in situ experiments requires a specialized sample environments and high stable instrumentation. The data analysis can also become complex because diffraction patterns continuously evolves with time. Despite these challenges, in situ XRD remains one of the most powerful tool for understanding the dynamic materials behavior. The major advantage of this in situ characterization is that it connects the structure, dynamics, and functionality under realistic conditions. The key performance indicator here is the in situ XRD provides the real-time insights into the materials evolution. It enables the advanced research in energy materials, catalysis, thin films, optoelectronics, and nanotechnology. Thank you for attending this module on advanced X-ray diffraction analysis. In this course, we explored the fundamentals of Brag's diffraction, X-ray diffraction instrumentation, peak broadening analysis, crystallite size estimation, Williamson-Hall analysis, the importance of Rickwell refinement profile, defect analysis, and advances in situ XRD applications. The XRD remains one of the most essential characterization technique for understanding the crystalline materials and nanostructures. I hope this module provides you a strong conceptual understanding and practical insight into the advanced diffraction analysis. Thank you once again, and I wish you a success in your research journey.